Hello, hello! We are going to talk about phase change in this video. I really like talking about phase change because this example is pretty interesting, I think. So it's going to go over boiling, which everybody has experienced. And I think hopefully it should kind of explain this vapor dome we talked about in the last video, because I know after the last video everybody's always kind of confused because they don't really know how to apply any of that information. So hopefully this will give you a little bit better understanding about all of that. To go over this, we are going to talk about having water in a piston cylinder assembly. Water is going to start out at 20 degrees Celsius, and then we're slowly going to heat that water while keeping the pressure constant. And the pressure is going to be kept at a constant value of 1.014 bar, which is 14.7 psi. All right, and as we go through this, we're going to look at these vapor domes, and essentially we're going to be following a dot along some of the lines. Okay, so to get started, let's draw our scenario here. We're going to have a piston cylinder assembly. We're going to start out with liquid water. And this liquid water is just sitting here. It's at 20 degrees Celsius. We got a closed system. And we don't have a heat source at this time, right? So it's just sitting there in its natural state at 20 degrees. Okay. Now, keep this in mind. We'll come back to this in just a second. So what we're going to do is we're going to look at this vapor dome. Now this is that dome that was pulled off of that PVT surface diagram that we looked at before. Now if you'll notice, we've got some lines drawn on here. And each of these lines has a pressure associated with it. Okay, so any point on this bottom line, for instance, so if I were to pick a point here, or a point here, or a point over here, this line tells me what the pressure is. So the pressure at any point on this line is going to be 1.014 bar. This is a constant pressure line, also called an isobar. You've probably heard of isobars if you've watched the Weather Channel, because they always talk about the isobars. Right, so isobar is just a constant pressure line. So if I were to go on any point on this line right here, I know the pressure would be 10 megapascals. Okay, and notice the pressure values, we're starting out at 1 over here, and this one here is 30. So pressure is going to increase kind of as we move this way on the plot. Okay, so that's about isobars. Notice this is specific volume, this is temperature. We've got this critical point right here, and the pressure at this point is 22.09 megapascal. Remember, that is the highest pressure where you can have the saturated liquid and saturated vapor at the same time. We talked about that before in the last video. Okay. Now, this also kind of shows you what phases we've got. We've got liquid, we've got vapor, and in this dome we've got liquid vapor. All right, so this is a two-phase mixture right here, the liquid vapor mixture. All right, so that's going to be important to keep track of. Now, let's go ahead and let's talk about our little scenario here. Okay, so we've got liquid water, it's at 20 degrees. Here's 20 degrees, here we're going to be using this little point 1 right here. This is our initial starting point. So we don't have any heating, water's at 20 degrees. This point right here, since it's located outside of this vapor dome, this temperature is significantly less than the 100. One thing I forgot to point out, if you'll notice on this horizontal line in here, it gives this temperature. Temperature is going to be constant from this point F to this point G. And I'll tell you what these points are when we get down to number 2 here. But this is going to always be your boiling point. Okay, so your temperature right here. Now, for instance, if I went up to this 10 megapascal line in the tables, and I'll show you how to find it later on, but when you look up in the tables for 10 megapascal, it'll give you the temperature for the boiling point. And that would be the temperature at any point along this horizontal line. Okay, so we're going to cover this in a lot more detail as we go through using the tables and everything. But I just wanted to point out, this gives you boiling point. All right. So now back to our case. So we're at 20 degrees. Boiling point is 100 degrees at this pressure that we're at. Notice the boiling point changes with pressure. So if we have 10 megapascal, our temperature for boiling is going to be a lot higher. Okay, so our temperature is significantly less than the saturation temperature. That's just the fancy word for the temperature where boiling would start to occur. Okay, so let's write some of that out. At this point, since we're way below here, we can put the temp is lower than the saturation temp. So again, remember that's just where boiling would occur. We talked about saturation temperature in the last video. Remember, that's just going to be your temperature where you're going to have a phase change occur. So since our temperature is lower than that saturation temperature, it's not about to vaporize, it's not about to start boiling. We're going to say that this is a compressed liquid. Okay, so it's a compressed liquid. That's what we've got right here. Okay, and compressed liquid we'll talk about later because there are specific tables for compressed liquids. All right, but essentially what you need to know is you've got a temperature, it's lower than our saturation temperature, it's not about to vaporize. That gives you a compressed liquid. Okay, now what we're going to do is we're going to start to add heat. All right, so we're heating to 100 degrees Celsius. So we're going to add some heat here. So let's draw our little system again. So we got our piston, here's our water, and we're going to add heat. Okay, so the temperature is going to go up. Temperature is going to rise up to 100 degrees Celsius. So what we're doing is we're going to move our dot from point 1, we're going to move it up to this point F. All right, so that's where we're going. We're going to go up to point F right where it hits 100 degrees Celsius. Now, at this point, we've got what's called a saturated liquid. All right, and it's going to be called a saturated liquid because remember, when we have the term saturated or saturation, that implies to you that we're about to have a phase change. Okay, so a saturated liquid is a liquid that is about to vaporize. So essentially our liquid water is about to start to turn into vapor. Okay, and notice the temperature. All right, so it's 100 degrees Celsius. So that's the boiling point of water at your standard atmospheric pressure, okay, which is what we've got. So that's what that plot there is telling you. So if we go up to this point 1, or point F, where we've got the temperature of 100, we're on the verge of starting to vaporize. So we've got saturated liquid. Okay. Now, if you notice as we go from 1 to F, specific volume's not going to change too much. Okay. So let's put specific volume. Doesn't change much. And remember, specific volume is related to density. Okay. So that changes a little bit. Your temperature is increasing though. Okay. So the temp increases. And remember, we're raising the temperature at that constant pressure. So we're holding that pressure constant. That's why we're on this constant pressure line. Okay, and then we get to this point F. All right. Now, let's go to the next page. So the next page, when we get to that one, we're going to continue heating. Okay. Now, the cool thing is, remember we're starting at F right here. We're already at 100 degrees, right? And we're going to continue heating. What's going to happen though? The temperature is going to stay the same. It's going to stay at 100 degrees, even though we're still adding heat. All right, so we keep adding the heat there. What happens though is now we're going to vaporize that liquid water. So at this point we've still got some liquid water, but now we've also got water. Put water first. We got water vapor. Okay. Now we've got this mixture. We've got this liquid vapor mixture. Okay, but the cool thing is the temperature stays the same. It's going to be constant this whole way until we get over to the end of this vapor dome. All right, so it's pretty interesting, I think. So we're going to continue to add heat, and what happens is the energy here that gets sent into this system, it's used to vaporize that water. Okay, so F is going to, this point here, is going to move across this horizontal line, and let's say we stop somewhere right here. I don't know. We're going to stop somewhere in the middle there of that vapor dome. Okay, so we're producing water vapor now. We still have liquid water, so we've got this mixture. All right, so let's put, we've got additional heat at fixed pressure. And what happens is that results in vapor formation without a change in temperature. Okay, and this is because we're holding that pressure fixed. Okay, now your specific volume increases, which means density gets smaller. And we end up with a two-phase liquid vapor mixture. All right, so that's what we end up with at this point. Okay, but I think it's pretty interesting that if you hold that pressure constant, then your temperature is going to stay constant throughout this range during that vaporization process. Okay, so to me that's pretty interesting. Now, we have a term that we use to calculate how much vapor we've got relative to the total mass. Okay, and that's going to be called quality. So let's put that right here. And just to separate it out, I'll use a different color. That way it'll be easy to tell what goes with what. So quality is going to equal a ratio of mass of vapor to the total mass. So equation that we would have for this, our variable for quality is going to be X. All right, so anytime you see an X, this is talking about quality. So X is going to equal the mass for the vapor, so vapor mass, over your total mass. So this would be mass of the liquid plus that vapor mass. So this is quality. It's just a ratio. And quality, or X, is always going to be greater than, equal to 0, or less than equal to 1. Okay. Now, let's think about what this means. Let's go back up to this diagram here. At this point F, we are just about to vaporize. So we're still 100% water. Okay, it hasn't vaporized yet. It's just about to, but it hasn't yet. So at this point right here, X, or your quality, is going to be 0. And that's because we don't have any vapor mass yet. All right, so M vapor goes to 0. All right. Now over at this point G, which we're going to talk about more when we get down here, this point is at the end of this liquid vapor dome. So at this point, this is going to be where we have all vapor. Right? So here at this point, X, or your quality, is going to be 1. So here the vapor mass is 100%. Okay? So essentially your vapor mass equals the total mass. All right, so you're all vapor at this point. So X is 0, X is 1 at these two locations. Okay, so keep that in mind because you will need that later on. All right, but X is just telling you how much water vapor you've got in your mixture. All right, which is important to know. So now that we've got that talked about, let's go to 4. So now for 4, we're going to keep heating this. Going to keep going. And if we look at our little dot, we're going to move from here over to point G. Okay, so now we're at this point G. Now at this point here, let's draw our picture again. We've got our piston. Now we are all water vapor. Okay, 100% water vapor at this point. Okay. When we get to G. Now at this point, since we're now at this location, this is at the edge of this dome, this is going to be where we've got saturated vapor. Okay? And that's because phase change here is beginning or ending. Right? If you removed heat, you would start condensation. You would start returning back to liquid water. Okay? Think about it that way. So we added heat, and that gets us to point G. So this is the saturated vapor state. And like I said, if any heat is lost, condensation will start. Okay, now remember at this point, quality is 1 because we are 100% water vapor. Okay, so that's what this point G gives you. This is where we've got all water vapor. So point F, no water vapor yet. Point G, all water vapor. And throughout this whole time, temperature has been 100. Okay, now after we've gotten to 100% water vapor, then if you keep heating at this point, got one more of these. So if we keep heating at this point, you're still going to have 100% water vapor. All right, so that's not going to change. Still got this. And we still got heat being added like that. Okay, now what we're going to do though is we're going to move from G, we're going to move out along this line here. Okay, so eventually we get to this point S. Now this is what we have if we continue heating at a fixed pressure. So let's make sure we put that down. So continued heating, let's put at fixed pressure, just like before. So pressure stays at 1.014 bar. What we get when we get to this point is we're going to have what's called superheated vapor. Now notice here the temperature has started to change. Okay, so between F and G, temperature stayed the same as the water was vaporizing. Once it's already become water vapor, the temperature will now start to rise again. Okay, so at this point our temp is higher than the saturation temperature. Okay, and at this point, if we lost some heat, that vapor would not be ready to condense. So let's just put could lose heat without having condensation. All right, so it's not about to do a phase change at this point because we've added enough heat, temperature's high enough above this boiling point where you could lose some of it and you're not going to return to liquid water. Okay, so this is superheated vapor. Now later on when we get to the tables, which will be in the next video, we'll talk about compressed liquid tables, the liquid vapor tables, and then the superheated vapor tables. Okay, so we're going to have to be able to figure out which table we need to use. Okay, so you need to make sure you understand what's going on with this vapor dome because this is going to be important. Everything's going to come back to this. And we'll review it again as we go through the steam table section. But I just want to point out, you really need to understand that. All right. Now also notice here, and pointed out, that your specific volume here increases. Okay. And if we were to reverse this process through cooling using this same pressure, basically our dot would return along this exact same path. Okay, so we'd go from the superheated vapor to the liquid vapor mixture and then back down to compressed liquid. All right, so your path wouldn't change, you'd just be going in the reverse direction. Okay. Now, in this example, our pressure was fixed. It was 14.7 psi, which is 1 atmosphere. So that's like the standard atmospheric pressure. If our pressure was increased, boiling would occur at a higher temperature. And we see that right here. So if our pressure was at 10 megapascal, our temperature for boiling would be up here at this point. Okay, whatever that may be. So boiling depends on pressure. If pressure is fixed, then that boiling point is fixed. Okay? Important thing to realize there. And a couple more things, last two things. There's something called latent heat. And I want to tell you what it is in case you hear about it. Latent heat is just the amount of energy needed to melt a solid or vaporize a liquid. All right, so that's all that is. And if you hear of latent heat of fusion, then what that is, that's going to be the amount of energy released during freezing. Actually, no, I'm saying that wrong. I got two things on here. It's the amount of energy released during melting. Okay, and actually that also does equal the amount of energy released during freezing. Okay, so that's what that is. So latent heat, that's all those are. And at 1 atmosphere, so at standard atmospheric pressure, you need 333.7 kilojoules per kilogram of energy. All right, that's how much energy is released during melting or during freezing. All right, guys. So that should be enough for this video. It's 25 minutes. It's kind of a long video, but it is important to understand these vapor domes. We will revisit these in the next video over steam tables. I will see you guys later.